The eye evolved not once, not 10 times, not 20 times. By the latest count, no fewer than 40 times, completely independently in different lines of animals. 40 times evolution faced the same problem. 40 times it arrived at the same answer. But before we talk about how the eye appeared, we need to understand what came before it. And here is a question that seems simple until you start thinking about it seriously. When did the first true eye appear on Earth? Not the first cell capable of responding to light, the first organ capable of forming an image. An organ that allowed one creature to see another creature as an object in space. Because before that moment, there was no reason to have a shell, no reason to run, no reason to hide. The world was full of life, and nothing in it could be seen. Then, almost simultaneously by geological standards, everything changed. And that moment changed everything that came after it. Before we go any further, please take a moment to subscribe to this channel. It genuinely helps us continue making work like this. Thank you. To understand what the first eye was, you first have to understand what light is, and why it matters so much to living things that evolution kept reinventing ways to detect it over and over again across hundreds of millions of years. Light is electromagnetic radiation. It travels at approximately 186,000 miles per second through vacuum, which means that by the time you finish reading this sentence, light could have circled the Earth roughly 7 times. It arrives in discrete packets called photons, each carrying a specific amount of energy determined by its wavelength. The wavelengths we call visible light occupy a narrow band of the full electromagnetic spectrum, roughly between 400 and 700 nanometers, which is a range so small relative to the full spectrum that if you stretched the entire spectrum across the continental United States, from New York to Los Angeles, the slice we can see would be thinner than a credit card. This is worth keeping in mind as we go, because it means that what we experience as sight is, from the beginning, a profoundly limited window onto physical reality. But within that narrow window, light carries an extraordinary amount of information. It tells you the shape of objects, their distance, their motion, their color, their surface texture. It tells you whether something is approaching or retreating, whether it is large or small, whether it is alive or dead. No other physical signal available to organisms on this planet carries comparable information density at comparable speed. Sound is slower and attenuates quickly with distance. Chemical signals are slower still and drift unpredictably with currents and wind. Pressure waves require physical contact. Light arrives instantaneously from any direction, carrying a complete picture of the environment at the moment it was reflected. For any organism that could decode that information, the evolutionary advantages would be staggering. And life, given enough time and enough variation to work with, figured out how to decode it. Multiple times, on multiple independent occasions, starting from scratch each time. The story begins not with eyes at all, but with a single protein. Opsins are a family of light-sensitive proteins found in virtually every animal that has ever been studied. They are ancient, predating the split between major animal lineages by hundreds of millions of years. An opsin molecule works something like a mousetrap. It sits embedded in a cell membrane, holding a smaller molecule called retinal in a specific shape. When a photon of the right wavelength strikes the retinal molecule, the retinal changes shape, springing the trap. This shape change triggers a cascade of chemical reactions inside the cell, ultimately generating an electrical signal. The entire process, from photon absorption to electrical signal, takes less than 1/1,000,000,000th of a second. It is one of the fastest chemical reactions in all of biology. This is the molecular foundation of all vision, in every animal that has ever lived. It does not matter whether you are a fruit fly, a scallop, a mantis shrimp, a hawk, or a human being. The fundamental transaction, photon strikes retinal, retinal changes shape, electrical signal generated, is the same. Evolution did not reinvent the fundamental chemistry of light detection. What it reinvented, 40 separate times, was everything that sits on top of that chemistry. The housing, the optics, the neural processing, the integration of multiple light-detecting cells into a system capable of forming an image. The eye, in other words, is not just an opsin. It is everything that makes a single light-sensitive molecule into something that can tell you which direction danger is coming from. To appreciate how remarkable this achievement is, consider where life was for most of its history. The Earth is approximately 4.5 billion years old. Life, in the form of single-celled organisms, appears in the fossil record at least 3.5 billion years ago. For the first 3 billion years of that history, life remained almost entirely single-celled. There were no animals. There were no eyes. There was, however, light. And even single-celled organisms were responding to it. Euglena, a single-celled organism that has been around for hundreds of millions of years and is still alive today, has a structure called a stigma or eye spot, a small patch of orange-red pigment near the base of its flagellum. The stigma does not form images. It cannot tell Euglena what is out there in the world. But it can tell Euglena which direction the light is coming from, which is enough for a photosynthetic organism to orient itself toward the sun. This is the simplest possible form of photoreception. Not seeing, just sensing. And it is extraordinarily ancient. The critical conceptual distinction here is the difference between photoreception and vision. Photoreception means detecting the presence of light and perhaps its direction. Vision means forming an image. These are not points on a single scale, but qualitatively different capabilities. A smoke detector and a television camera are both electronic devices that respond to electromagnetic radiation, but they are not doing the same thing. A smoke detector tells you that something is happening somewhere. A television camera tells you exactly what is happening and where. The evolutionary journey from the stigma of Euglena to the compound eye of a Trilobite is something like the journey from a smoke detector to a high-definition camera. And understanding how that journey happened requires understanding why forming an image is such a difficult problem to solve. The fundamental challenge is this. A single light-sensitive cell, no matter how sophisticated its chemistry, can only tell you one thing: how much light is hitting it right now. That is useful information, but it is not an image. To form an image, you need to know not just how much light is arriving, but where it is coming from. You need, in principle, a separate light-sensitive cell for every direction you want to distinguish. If you want to resolve an image into 1,000 distinct points, you need at least 1,000 distinct photoreceptive cells, each oriented in a slightly different direction, each reporting independently on the light arriving from its particular slice of the visual field. And then you need neural processing capable of integrating all those individual reports into a coherent picture of the world. This is an enormously complex engineering problem. The fact that evolution solved it 40 separate times is not a coincidence. It is a statement about how powerful the selective advantage of good vision is. The earliest fossil evidence for eyes comes from the Cambrian period, which began approximately 539 million years ago. What makes the Cambrian so remarkable and so central to the story of vision is that complex eyes appear in the fossil record almost simultaneously with the first complex animals. There is essentially no fossil record of a gradual, stepwise evolution of the eye from simpler precursors, at least not in the macroanatomical sense. Instead, you have hundreds of millions of years of eyeless life, and then, within what geologists call a geological instant, a span of perhaps 20 million years out of 500 million, you have trilobites with sophisticated compound eyes, anomalocarids with stalked eyes bearing thousands of individual lenses, and the ancestors of most major animal lineages all appearing more or less at once. This explosive appearance of complex body plans, including complex visual systems, in a geologically brief window is the Cambrian explosion, and it is one of the most intensely debated events in the history of life. Andrew Parker, a biologist at Oxford, proposed in 2003 a hypothesis that has become known informally as the light switch theory. Parker's argument was not that eyes caused the Cambrian explosion in any simple, direct sense, but that the appearance of the first image-forming eyes fundamentally transformed the ecological dynamics of the Cambrian Ocean in ways that triggered an arms race of body plans, and that this arms race was the engine driving the sudden appearance of armor, teeth, claws, and the entire architectural vocabulary of complex animal life. The logic runs like this. Before image-forming vision, predation was possible but inefficient. A predator without eyes must locate prey by touch, by chemical gradient, by pressure waves in the water. These are slow, short-range, unreliable methods. A predator with eyes can locate prey from a distance, can pursue moving targets, can distinguish between worthwhile prey and inedible objects, and can plan intercept trajectories. The first predator with image-forming vision would have had an advantage so overwhelming that it would have driven prey populations to evolve countermeasures, which would have driven further predatory evolution, which would have driven further defensive evolution in the escalating spiral of the arms race that we see written in the fossil record of the Cambrian.
The evidence Parker cited for his theory was partly anatomical and partly geological. Anatomically, the very first complex Cambrian animals appear with both sophisticated visual systems and sophisticated defensive armor, essentially simultaneously in the fossil record, which is exactly what you would expect if the appearance of vision triggered an arms race, rather than if vision evolved gradually in an already complex ecological landscape.
Geologically, Parker pointed to the unusual quality of Cambrian fossil preservation, which shows that Cambrian organisms had transparent tissues in abundance, a feature consistent with a world in which being seen was suddenly a matter of life and death, and in which transparency was an evolutionary response to the existence of eyes. The theory remains controversial, as good theories tend to do, but it has changed the way many researchers think about why the Cambrian explosion happened when it did, rather than earlier or later. The most spectacular eyes from the Cambrian belong to Anomalocaris and its relatives, the radiodonts. We have discussed Anomalocaris before in this series, and if you have not seen that video, the short version is that Anomalocaris was the apex predator of the Cambrian Ocean, reaching lengths of perhaps 1 meter or more in a world where most other organisms were measured in centimeters. Its eyes, preserved in exceptional detail in fossils from the Burgess Shale and the Chengjiang deposits of China, were compound eyes, composed of many individual optical units called ommatidia, each unit contributing a single pixel to the overall image the animal saw. The Anomalocaris eyes were enormous relative to its body, stalked, and contained an estimated 16,000 individual ommatidia. For comparison, a modern housefly has approximately 4,000 ommatidia. A dragonfly, which is considered to have among the most sophisticated compound eyes of any living insect, has approximately 30,000. Anomalocaris, 520 million years ago, was already operating in the same league as a dragonfly. This is not a primitive eye. This is a sophisticated, high-resolution, wide field of view imaging system built by natural selection before the first fish had appeared, before the first land plant had taken root, before the continents had arranged themselves into anything resembling their current configuration. But the radiodonts were not alone in their visual sophistication. The trilobites, those ubiquitous arthropods of the Paleozoic era that persisted for nearly 300 million years before their final extinction at the end of the Permian, developed eyes of a kind that has no exact modern parallel. Trilobite eyes were compound eyes, like those of Anomalocaris and like those of modern insects, but they were built from a material that is, to put it plainly, remarkable. Trilobite lenses were made of calcite, a crystalline form of calcium carbonate, the same mineral that makes up limestone and chalk. This is not how any modern animal makes its lenses. Modern compound eyes use organic materials, proteins folded into specific shapes, to create their refracting structures. Trilobites used a mineral, and they did not use it clumsily. Paleontologists examining trilobite eye fossils have found that the calcite crystals in the lenses were oriented in precise, specific directions to minimize the optical aberration caused by the double refracting property of calcite. Trilobites were not just using calcite because it was available. They were using it in a way that required sophisticated optical engineering, exploiting a specific crystallographic property of the mineral to produce a lens with minimal distortion. In some species, the lenses show a design that was independently re-derived by the mathematician René Descartes in the 17th century as the theoretically optimal shape for minimizing spherical aberration. Trilobites had directions about by the Ordovician period, roughly 450 million years ago. The question of how eyes evolved from a simple photoreceptive patch to a sophisticated imaging system was, for most of the 19th century, considered one of the strongest objections to Darwin's theory of their natural selection. Darwin himself worried about it openly in On the Origin of Species, writing that it seemed absurd to suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances, for admitting different amounts of light, and for the correction of spherical and chromatic aberration, could have been formed by natural selection. Darwin went on to argue that it could have been, but the admission that it seemed absurd was honest, and it reflected a genuine difficulty in understanding how a structure as complex as the vertebrate eye could have evolved incrementally, given that each intermediate step would need to be functional and advantageous. The resolution to this apparent paradox came from the work of Dan Erik Nilsson and Susanna Pelger, two Swedish biologists who published a landmark paper in 1994, calculating the minimum time required for a light-sensitive patch of cells to evolve into a fully functional camera-type eye through gradual, stepwise improvement. Their model was deliberately conservative, assuming small, incremental changes of less than 1% per step, and requiring that each step improve visual performance by a measurable amount. The result was startling. Under their assumptions, the number of generations required to evolve a complete eye from a light-sensitive patch was approximately 360,000. In a species that reproduces annually, this is 360,000 years. In a species that reproduces more rapidly, it could be far less. Geologically, this is essentially instantaneous. The apparent paradox of eye evolution was not a paradox at all. The eye could evolve from scratch in a time so short that it would leave essentially no trace in the fossil record, which is precisely why we do not see a gradual fossil record of eye evolution. The eye evolves too fast to fossilize its own history. This calculation also helps explain why eyes evolved 40 separate times rather than once. If evolving an eye from scratch took hundreds of millions of years, you would expect it to happen once, or perhaps a handful of times in exceptional circumstances. But if it takes 360,000 years, and if the selective advantage of having an eye is massive in almost any ecological context where light is available, then you would expect eyes to evolve repeatedly, independently, in any lineage that has the basic Opsin chemistry in place and finds itself in a lit environment under predatory pressure. This is exactly what the fossil and molecular record shows. Eyes are not a single improbable invention. They are a predictable outcome of natural selection acting on organisms with Opsin chemistry in the presence of light and predation. The 40 independent origins of the eye are not 40 separate miracles. They are 40 separate applications of the same inevitable algorithm. The story of how scientists actually figured out that eyes evolved 40 separate times is itself a story worth telling, because it did not happen the way you might expect. For most of the 20th century, the prevailing assumption among biologists was that eyes had evolved independently, somewhere between 40 and 65 times, based purely on anatomical comparisons. Researchers looked at the eye of an insect, looked at the eye of a vertebrate, looked at the eye of a scallop, and concluded that these structures were so different from one another in their detailed anatomy that they must have arisen from completely separate evolutionary starting points. The compound eye and the camera eye use different optical principles, different cellular architectures, different developmental pathways, and different neural wiring. The conclusion that they were independent inventions seemed inescapable. Then, in 1995, a research group led by Walter Gehring at the University of Basel published a paper that appeared to overturn this entire picture. Gehring's group had been studying a gene called PAX6, which was known to be essential for eye development in mammals. Mice with a damaged PAX6 gene develop without eyes. The surprising discovery was that PAX6 was not a mammalian speciality. It was present in almost identical form in flies, in worms, in sea squirts, in nearly every animal lineage that had been examined. And in every case where it was found, PAX6 was doing the same job, controlling the development of whatever light-sensing organ that animal possessed. The PAX6 gene appeared to be a universal master control gene for eye development, present in the common ancestor of all animals and conserved across 600 million years of evolutionary divergence. Gehring went further. His group showed that if you took the mouse version of PAX6 and artificially activated it in a developing fruit fly at a location where eyes do not normally form, such as the leg or the wing, you would get ectopic eyes growing in that location. Not mouse eyes, fruit fly compound eyes. The mouse gene was able to trigger the entire developmental program for the fruit fly eye, even though the two eyes look completely different and were assumed to have evolved completely independently. The implication was startling. Either eyes had evolved only once, from a common ancestor that possessed PAX6 and some primitive light-sensing structure, and all subsequent eye diversity was modification of that original design, or PAX6 was a much more ancient regulatory gene that was repeatedly co-opted during independent eye evolution events because it happened to be the most useful available control element for coordinating the development of light-sensing structures. Gehring argued for the first interpretation, claiming that the existence of PAX6 across all animal eye types was evidence for a single evolutionary origin of the eye. The debate that followed was one of the more interesting disputes in modern evolutionary biology, and it has not been fully resolved. The current consensus leans toward a middle position. PAX6 is genuinely ancient, predating the divergence of major animal lineages, and it was probably involved in some primitive light-sensing function in the common ancestor of bilaterian animals. But the structural complexity of camera eyes, compound eyes, mirror eyes, and pit eyes is so different in their detailed organization that these architectures almost certainly represent independent evolutionary elaborations of that primitive PAX6-controlled light-sensing capacity, rather than modifications of a single ancestral eye design. The eye did not evolve once, but it evolved from a common molecular toolkit, which is why the same regulatory gene appears across such diverse eye types. Evolution, characteristically, built many different houses using the same foundation. This discovery reframed the question of eye evolution in a way that made it simultaneously simpler and more philosophically interesting. The question is no longer simply how many times did the eye evolve, with the answer being somewhere between once and 40, depending on how you count. The question becomes, given a common molecular toolkit, including Opsin and PAX6, and the basic cellular machinery for photoreception, how many different architectural solutions did evolution find to the problem of forming an image? And the answer to that question is genuinely around 40, including solutions so different from one another that they represent fundamentally distinct engineering approaches to the same optical problem. The unity is in the chemistry. The diversity is in the architecture. And the diversity is what reveals just how many ways there are to solve the problem of seeing. One of the most illuminating examples of this architectural diversity is the pinhole eye. A design so simple that it seems almost too primitive to be useful, and yet sophisticated enough to have been independently invented by at least two very different groups of organisms. The nautilus, a cephalopod that has remained essentially unchanged for hundreds of millions of years, has eyes that contain no lens whatsoever. Each eye is simply a fluid-filled chamber with a small opening at the front, working on exactly the same principle as a pinhole camera. Light enters through the pinhole aperture and projects an inverted image onto the retina at the back of the chamber. The image is dim because only a small fraction of available light passes through the small aperture, and its resolution is limited by the size of the aperture and the diffraction of light passing through it. But it works. The nautilus uses its pinhole eyes to navigate its environment and to detect predators. Given that the nautilus lineage has been using this design for at least 250 million years, without apparently feeling any evolutionary pressure to upgrade to a lens-based system, the pinhole eye is clearly adequate for the ecological demands of a nautilus's life, even if it would be hopelessly inadequate for the demands of ours. The chiton, a group of primitive mollusks covered in articulated armor plates, has taken the concept of distributed vision to an extreme that seems almost implausible. Chitons have hundreds of tiny eyes embedded directly in their shell plates, not in soft tissue around the shell as in scallops, but literally within the mineral structure of the plates themselves. The lenses of chiton eyes are made of aragonite, a crystalline form of calcium carbonate, similar to the calcite lenses of trilobites, but chemically distinct. The aragonite lenses are integrated into the shell material, with the underlying photoreceptors accessed through channels that pass through the shell plate. A chiton's eyes are essentially windows cut into its armor, looking out through holes in its shell. The entire visual system, lenses, photoreceptors, and neural connections is built into what would otherwise be a purely defensive structure. The chiton simultaneously wears its armor and looks through it. It is a design that requires the shell material to serve double duty as both structural defense and optical element. And the aragonite lenses have been refined by natural selection to the point where they provide useful spatial resolution despite being made of the same mineral as the animal's shell. The evolution of color vision adds another layer of complexity to this already intricate story. Color vision, as we experience it, depends on having at least two types of photoreceptors with different spectral sensitivities, so that the color of a light source can be determined by comparing the relative stimulation of the different receptor types. A single photoreceptor type, no matter how sophisticated, is fundamentally colorblind because it cannot distinguish between a bright light of one wavelength and a dim light of another wavelength that happens to stimulate the receptor equally strongly. This is the principle of univariance, and it means that color perception requires multiple photoreceptor types as an absolute minimum. Most mammals, including dogs and cats, have two types of cone photoreceptors, giving them what is called dichromatic color vision. They can distinguish colors, but their color space is simpler than ours. The ancestral mammals appear to have been nocturnal, and many of the photoreceptor types present in the common ancestor of vertebrates were subsequently lost during the nocturnal bottleneck of mammalian evolution, when color vision was less useful than high sensitivity in dim light. Primates subsequently re-evolved trichromatic color vision through a relatively recent gene duplication event that produced two red-sensitive cone types from a single ancestral long-wavelength sensitive cone. This re-evolution of trichromacy in primates is thought to be related to the importance of detecting ripe fruit against green foliage, which requires the ability to distinguish red and orange from green, a discrimination that is difficult with only two cone types. Birds, fish, and reptiles generally retained the ancestral tetrachromatic color vision that mammals lost, with four cone types providing a color space richer than our own and extending into the ultraviolet. A bird looking at a flower sees a different flower than we see, with ultraviolet patterns invisible to us that may guide its foraging or its assessment of potential mates. A male bird that appears to have a modestly coloured plumage to our eyes may display elaborate ultraviolet iridescence that is visible to female birds of the same species and plays a central role in mate selection. We have been studying bird behaviour for centuries, and we have only recently realised that we have been missing a significant fraction of the visual information that birds are exchanging with each other, simply because our own visual system lacks the hardware to receive it. The evolution of high spatial resolution, the ability to resolve fine detail at a distance, is a separate challenge from colour vision and has been solved in different ways by different lineages. In camera-type eyes, spatial resolution depends primarily on the density of photoreceptors in the retina and the optical quality of the lens. In the center of the human retina is a region called the fovea, a small pit approximately 1.5 millimeters in diameter containing approximately 150,000 cone photoreceptors per square millimeter, the highest density of any region of the retina. When you look directly at something, you are pointing your fovea at it, bringing the highest resolution region of your retina to bear on whatever you are trying to examine closely. This foveal concentration of photoreceptors is the reason why you can read text at a comfortable distance, but cannot read text in your peripheral vision, even though your peripheral retina contains photoreceptors and is certainly doing something. Your peripheral vision is optimized for detecting motion and for providing a wide-field situational awareness rather than for resolving fine detail. Birds of prey take foveal concentration considerably further than humans do. The fovea of a hawk or an eagle may contain 1 million photoreceptors per square millimeter, roughly 7 times the density of the human fovea. Some raptors have 2 foveas, one pointing forward for binocular depth perception and one pointing sideways for monocular detection of movement. The visual acuity of a red-tailed hawk has been estimated at approximately 8 times human acuity, meaning that the hawk can resolve detail at a distance of roughly a quarter mile that a human with normal vision could only resolve from roughly 30 yards. A hawk circling at altitude is not searching vaguely for something small moving below. It is reading the landscape with the resolving power of a telescope, detecting the movement of a mouse in grass from a height at which the mouse would be invisible to us. The jumping spider takes yet another approach to the problem of high resolution with limited neural resources. Jumping spiders have 8 eyes arranged around their head, but the 2 large, forward-facing principal eyes are the ones that have attracted the most scientific attention. These eyes are camera-type eyes with extremely high spatial resolution in a narrow central field, achieved through a retina containing an exceptional density of photoreceptors in a very small region.
The catch is that the principal eyes of jumping spiders have virtually no ability to move within the head, because they are fixed within the exoskeleton. Instead, the retinas within the eyes can be moved by muscles, scanning across the narrow, high-resolution field to build up a composite image of the scene in front of the spider. The effect is something like a spotlight scanner, with the narrow beam of high resolution sweeping back and forth to cover a region that would otherwise require a much larger and more expensive eye to image at once. The jumping spider has solved the problem of high resolution with limited resources by turning its retinas into moving parts, a solution that is as mechanically elegant as it is biologically unusual. The diversity of eye designs that resulted from these 40 independent origins is, when you examine it closely, one of the most extraordinary catalogues of biological engineering on the planet. The basic problem of forming an image can be solved in at least half a dozen fundamentally different ways, and evolution has tried most of them. The 2 most familiar to us are the compound eye, as seen in insects and crustaceans, and the camera type or single lens eye, as seen in vertebrates and cephalopods. But these are not the only options, and in some cases not the best options for particular ecological situations. The camera type eye works on the same principle as a camera. Light enters through a small aperture, is focused by a lens onto a light-sensitive surface, and the resulting image is recorded. The advantages of this design are high spatial resolution and good performance in a range of lighting conditions. The disadvantages are a limited field of view and the problem of the blind spot, the point where the optic nerve exits the retina and where there are no photoreceptors. The vertebrate eye has this blind spot. You can demonstrate it right now by closing your left eye, holding your right hand at arm's length with your thumb extended, focusing on the thumb, and then slowly moving a finger of your left hand from the side into your visual field. At a specific position, your finger will disappear, not because it has moved behind your thumb, but because its image has fallen on your blind spot. You have a hole in your visual field that your brain fills in with plausible-looking background. You are, at this moment, partially hallucinating. Your visual system is so good at gap filling that you have probably never noticed it. The cephalopod eye, found in octopuses, squid and cuttlefish,
is superficially almost identical to the vertebrate eye. Same overall camera architecture, same pupil, same lens, same retina. But it evolved completely independently, and it has one significant advantage over the vertebrate eye. Cephalopod photoreceptors face toward the light rather than away from it, as vertebrate photoreceptors do. This means the cephalopod eye has no blind spot. The optic nerve exits from the back of the eye rather than through the retina. It is, in this specific respect, a better designed eye than yours. When the biologist Richard Dawkins pointed this out, he described the vertebrate retina as wired in backwards, which is strictly accurate as a description of the anatomy, even if the vertebrate eye functions superbly well despite this apparent design flaw. The backwards wiring of the vertebrate retina is a consequence of the embryological origin of the eye from outgrowths of brain tissue, a developmental history that locked in the inverted arrangement long before vertebrate eyes reached their current level of sophistication. The compound eye of insects and crustaceans takes a completely different architectural approach.
Rather than one large aperture and one large focusing element, the compound eye uses thousands of tiny apertures, each with its own tiny lens and its own small cluster of photoreceptors, each pointing in a slightly different direction, together building up a mosaic image of the environment. The advantage of this design is an enormous field of view, often approaching 360 degrees, and an exceptional ability to detect motion, since any moving object will cross many individual ommatidia in rapid succession, generating a strong neural signal. The disadvantage is relatively low spatial resolution compared to a camera-type eye of similar size, because each ommatidium contributes only a single pixel to the image, and the angular separation between adjacent ommatidia limits the finest detail the eye can resolve. A dragonfly's 30,000 ommatidia give it excellent compound eye resolution, but still far coarser than the 120 million photoreceptors in a human retina. What a dragonfly lacks in resolution, it more than compensates for in other ways. Its compound eyes cover nearly the entire sphere around its head, leaving almost no blind zone. Its visual system is optimized for detecting and tracking rapidly moving targets, which is an obvious advantage for an aerial predator that catches prey on the wing. Studies have shown that dragonflies successfully intercept their prey in approximately 95% of attempts, a success rate that surpasses that of lions, sharks, and most other predators we regard as superbly effective hunters. Much of this success comes from the dragonfly's visual system, which can calculate the future position of a moving target and direct the dragonfly on an interception course rather than a pursuit course, a cognitively sophisticated behavior implemented in a brain the size of a sesame seed. The scallop takes yet another approach, one so bizarre that it seems more like science fiction than biology. Scallops have eyes, dozens of them, arranged along the edge of the mantle. Small, bright blue structures that peer out at the world when the shell is open. What makes scallop eyes genuinely extraordinary is not the number, but the optics. Each scallop eye is a reflecting telescope, not a refracting telescope, which uses a lens to bend light to a focus, but a reflecting telescope, which uses a curved mirror to reflect light to a focus.
This is the same optical principle used by the Hubble Space Telescope and by most large professional astronomical observatories. The scallop eye achieves this with a mirror made of guanine crystals, the same molecule that is one of the 4 bases of DNA, arranged in precise layers to form a curved reflector. The image is focused onto a retina that is divided into 2 regions, one for central vision and one for peripheral vision, each using different types of photoreceptors. The scallop has independently invented astronomical telescope optics. It did this hundreds of millions of years ago. It uses this optical system to detect the shadows of approaching predators, primarily sea stars, and to initiate its escape response, which involves rapidly clapping its shell to jet away through the water. The scallop is not looking at the world with curiosity. It is running a continuous early warning system, and the mirror-based telescope optics are precision engineering in the service of survival. If the scallop represents one extreme of optical creativity, the mantis shrimp represents another. Mantis shrimps are crustaceans that live in tropical marine environments, and they are visually the most complex animals on Earth, by almost any measure you care to apply. A human eye has 3 types of photoreceptors, sensitive to red, green, and blue light respectively. We combine the signals from these 3 types to perceive the full range of colors we see. Most birds have 4 types of photoreceptors, adding ultraviolet sensitivity to the 3 color channels of mammals. The mantis shrimp has 16 types of photoreceptors. 16. When researchers first discovered this, the assumption was that mantis shrimps must experience a spectacularly rich color vision, perceiving distinctions invisible to any other animal, seeing a world of color complexity that we could not begin to imagine. The reality, when it was finally worked out, turned out to be both more surprising and more philosophically interesting than that. Mantis shrimps are actually worse at distinguishing between similar colors than humans are. In controlled experiments, they failed to discriminate between shades that a human would find obviously different. The 16 photoreceptor types are not being used for spectral discrimination in the way that our 3 types are. Instead, researchers now believe that the mantis shrimp visual system is doing something more like color recognition than color discrimination. Rather than comparing signals across photoreceptor types to identify colors the way a human does, the mantis shrimp appears to use its 16 photoreceptor types as a set of discrete labeled categories, each matching specific wavelengths to specific signals without comparison or mixing. The effect is something like having 16 keys on a keyboard, each producing a labeled note, rather than having a full keyboard and the ability to hear the relationships between notes. It is a fundamentally different computational approach to the problem of color, and it may allow the mantis shrimp to process color information faster and with less neural computation than a comparison-based system would require. Whether this is better or worse than human color vision depends entirely on what you are using it for. For a predator that needs to make instant life or death decisions about the color of things it encounters, a fast recognition system may be more useful than a nuanced discrimination system. Beyond the 16 photoreceptor types, the mantis shrimp visual system adds sensitivity to ultraviolet light, to polarized light, and to circularly polarized light, a type of light that almost no other animal can detect. Circularly polarized light is reflected from the shells of certain crustaceans and from some bioluminescent organisms, and the mantis shrimp uses its ability to detect it as a private communication channel. Some mantis shrimp species have body markings that reflect circularly polarized light, visible only to other mantis shrimps and invisible to predators and competitors that lack the necessary photoreceptors. They are conducting private conversations in a wavelength of light that their predators literally cannot see. This is an arms race applied to the electromagnetic spectrum itself. Evolution creating private channels of communication by exploiting physical properties of light that most other organisms cannot access. Polarized light vision is actually more widespread than most people realize. Many insects, cephalopods, and crustaceans can detect polarized light, and they use it for a variety of purposes. Bees use the polarization pattern of skylight for navigation, which allows them to determine the position of the sun even on overcast days when the sun itself is hidden behind clouds. Octopuses appear to use polarization sensitivity to see contrast in environments where color contrast is minimal. Certain species of fish use polarized light to detect transparent prey in open water, a prey item that would be essentially invisible to an eye relying on color or intensity contrast alone. Polarized light vision is another example of evolution finding a physical property of light that carries information and building biological hardware to decode that information. Ultraviolet vision is similarly widespread. Most insects, many birds, and some fish and reptiles can see in the ultraviolet range. Flowers that appear uniformly yellow to human eyes often show dramatic ultraviolet patterns visible only to bees, patterns that function as landing guides pointing toward the nectar at the center of the flower. The flower and the bee are communicating in a channel of light that is invisible to most of the animals that share their environment. Birds that appear dull and uniformly colored to human observers often show dramatic iridescent patterns in the ultraviolet, patterns that play a role in mate selection and species recognition. Many animals are conducting their visual lives in a layer of reality that we literally cannot see, using frequencies of light that evolution discovered long before we built instruments sensitive enough to detect them. The visual world of fish deserves extended attention because fish have been doing sophisticated things with light for far longer than any terrestrial animal, and the range of visual solutions found in fish is correspondingly wide. Fish were the first vertebrates, and the vertebrate eye reached a high degree of optical sophistication very early in fish evolution. The camera-type eye of a fish is fundamentally similar in its organization to the camera-type eye of a human, with a cornea, a lens, a retina containing multiple photoreceptor types, and an optic nerve connecting to a visual processing center in the brain. But there are differences that reflect the very different optical challenges of living underwater. Water has a higher refractive index than air, which means that the cornea, which does most of the focusing work in the human eye precisely because light crosses the air-cornea interface and bends significantly, does almost no focusing work in the fish eye. A fish's cornea is immersed in water on both sides, and so there is almost no refractive index difference at the cornea surface and almost no bending of light there. All the optical power in a fish eye must come from the lens. Fish lenses are consequently much more powerful and much more spherical than mammalian lenses, and they are made of materials with a carefully graded refractive index that increases from the outside to the center. A gradient index design that minimizes spherical aberration without the need for the aspherical lens shapes that vertebrates with air-cornea interfaces use. The gradient index fish lens was independently discovered by optical engineers in the 19th century and is now used in some fiber optic systems. Fish had been using it for 400 million years. Fish that live in different light environments have evolved dramatically different photoreceptor complements. Deep-sea fish often have only rod photoreceptors, the type specialized for dim light detection, with no cone photoreceptors at all, because in the near-complete darkness of the deep sea, there is no meaningful color information to extract, and every available photon needs to go toward building even a minimally adequate image. Many of these fish have rod photoreceptors with peak sensitivity shifted toward the blue end of the spectrum, matching the wavelengths of light that penetrate deepest into the ocean and the wavelengths of bioluminescence produced by many deep-sea organisms. Some deep-sea fish have evolved multiple banks of rod photoreceptors stacked on top of each other, each bank contributing its signal to the same neural pathway, in an arrangement that effectively multiplies the photon-catching capacity of the retina without increasing its area.
At the other extreme, fish living in the highly illuminated and colorful environments of coral reefs often have more cone types than humans do, with some species having sensitivity extending into the ultraviolet at one end of the spectrum and toward the red and near-infrared at the other. The coral reef is among the most visually complex environments on Earth, with thousands of species displaying elaborate color patterns that serve as species identification, mate attraction, territorial warning, and camouflage signals simultaneously. The visual systems of reef fish have co-evolved with this complexity, developing spectral sensitivities tuned to the specific color signals most relevant to their ecological situation. A fish that feeds on particular invertebrates may have photoreceptors specifically tuned to detect the colors those invertebrates display. A fish that needs to recognize members of its own species among dozens of similar-looking species may have color vision optimized for the specific spectral differences that distinguish its species from its neighbors. The archerfish takes visual processing in fish to a remarkable extreme that has only recently been fully appreciated. Archerfish are predators that hunt insects above the water surface by spitting jets of water to knock them down. The challenge this creates for their visual system is considerable. An archerfish looking up through the water surface at an insect above it must compensate for the refraction of light at the water-air interface, which bends light rays and makes objects above the surface appear to be in different positions than they actually are. The archerfish must calculate where to aim its water jet, not at where the insect appears to be, but at where the insect actually is, accounting for the refraction that is distorting its perception. Furthermore, the archerfish aims from a position below the surface, while the water jet travels above it, requiring a three-dimensional trajectory calculation in an environment where the visual geometry is complicated by refraction. Archerfish perform this calculation with remarkable accuracy, hitting targets at distances of several feet with a success rate that implies genuine geometrical computation rather than simple learned approximation. Recent research has shown that archerfish can even recognize human faces, a task previously thought to require the large neocortex of mammals, suggesting that the neural processing power available to fish has been underestimated. The evolution of vision in cephalopods, the group that includes octopuses, squid, and cuttlefish, represents one of the most striking examples of convergent evolution in all of biology. And it also contains one of the most counterintuitive discoveries about color vision ever made.
Cephalopods have large, sophisticated camera-type eyes that rival vertebrate eyes in their optical quality. And, as we noted earlier, they are actually better designed in some respects, lacking the backwards photoreceptor arrangement and the blind spot that characterize vertebrate eyes. What cephalopods do not have, as far as anyone could determine from examining their photoreceptors, is color vision. They appear to have only a single type of photoreceptor, which, by the principle of univariance, means they should be completely colorblind. They should see the world in shades of grey. This created a paradox. Octopuses, cuttlefish, and squid are among the most spectacular color changes in the animal kingdom. Cuttlefish can ripple complex patterns of color across their skin in fractions of a second, using chromatophore cells that expand and contract to reveal or conceal pigment layers below. They use these color patterns for camouflage, for communication with potential mates, for warning signals to rivals, and for what appears to be active deception of prey. They are making sophisticated decisions about color that seem to require color perception. How can an animal that is apparently color blind produce and respond to such complex color patterns? The solution to this paradox, proposed in 2016 by a group of researchers including Christopher Stubbs and his colleagues, is as elegant as it is unexpected. The researchers noted that cephalopod pupils are not simple round apertures like human pupils. They are irregular, often taking the form of a W shape or a dumbbell shape or other asymmetric forms that seem unnecessarily complicated if their only function is to control the amount of light entering the eye. The researchers proposed that these irregular pupils act as spectral filters of a kind, using the chromatic aberration of the eye's lens to sort light of different wavelengths onto different parts of the retina. Chromatic aberration is a well-known optical defect in which a lens focuses different wavelengths of light at slightly different distances, so that the focal plane for blue light is closer to the lens than the focal plane for red light. In a human eye, this aberration is minimized by the design of the lens. In a cephalopod eye, the irregular pupil shape may be exploiting this aberration rather than minimizing it. By comparing the sharpness of focus in different parts of the visual field, the cephalopod might extract wavelength information from a single photoreceptor type that it uses to determine the color of objects. It would be colorblind in the conventional sense, but might achieve a functional equivalent of color discrimination through a completely different computational route. The animal that changes color most dramatically in the ocean may be solving the problem of seeing color through a mechanism that has no equivalent in any other visual system known to science. The question of how nervous systems process visual information has become, in the past 2 decades, one of the most productive frontiers in all of neuroscience. The retina itself, which might seem like a simple light-detecting array, turns out to be an astonishingly sophisticated signal-processing device. The human retina contains not just photoreceptors, but at least 5 distinct classes of neurons organized into 2 synaptic layers, performing substantial computation before any signal reaches the optic nerve. The retina detects edges, enhances contrast, performs motion detection, adjusts its own sensitivity over a 1,000,000-fold range of light intensities, and extracts multiple parallel streams of information from the raw photoreceptor signals, all before sending anything to the brain. Each of the roughly 20 distinct types of retinal ganglion cells, the neurons whose axons form the optic nerve, carries a different type of pre-processed visual information. Some types respond only to light turning on, others respond only to light turning off. Some are specialized for detecting motion in a specific direction. Others signal the color of light in their receptive field. The brain does not receive a raw image from the retina. It receives a pre-processed, multi-channel data stream in which much of the initial analysis has already been completed by the neural circuits of the retina itself. This discovery that the retina is a processor rather than a passive sensor had significant implications for our understanding of how visual experience arises. If the retina is already extracting specific features from the visual scene before the brain is involved, then the brain is not working with raw sensory data at all. It is working with a curated, pre-analyzed report in which certain features have been emphasized and others suppressed. This means that what we see is shaped not just by the neural processing of the brain, but by the architectural decisions built into the retina over 400 million years of evolution. The visual system you are using right now is not a general-purpose camera that could, in principle, be set up to detect any aspect of the visual scene. It is a specialized detector, optimized by evolution to detect specific features that were relevant to the survival of your primate ancestors, and necessarily blind to features that were not. The retina has already decided, before you consciously attend to anything, what is worth bringing to your attention. The most profound insight from studying the diversity of visual systems across the animal kingdom is perhaps this: there is no single correct way to see. Every visual system represents a set of trade-offs, a decision about which aspects of the electromagnetic environment are worth investing neural resources in detecting and processing, and which can be safely ignored. The human visual system made one set of trade-offs. The mantis shrimp made a different set. The jumping spider made another. The deep-sea fish, the hawk, the bee, the migrating warbler, the pit viper, and the scallop each made their own set, each tailored by natural selection to the specific ecological demands of their particular way of life. There is no view from nowhere, no God's eye view that sees everything. Every visual system is a perspective, a particular set of windows open onto physical reality, with other windows necessarily closed. The world as it is seen is always the world as it is seen from somewhere in particular, by an eye that was built for purposes that may have nothing to do with seeing the world as it actually is. This is a conclusion with implications that reach well beyond biology. If the visual systems of different animals represent genuinely different perspectives on physical reality, then the question of what the world looks like, really looks like, independent of any observer, becomes surprisingly difficult to answer. The physicist would say that the world is made of quantum fields and that color does not exist in the quantum fields themselves, only in the interaction between those fields and visual systems of particular designs. The philosopher would say that perception is not a window onto reality, but a construction, a model built by a nervous system for the purpose of guiding behavior in a particular ecological context. Both are pointing toward the same uncomfortable conclusion. The vivid, richly colored, three-dimensional visual world you experience is not simply there, waiting to be seen. It is produced. It is a creation of your visual system, shaped by 400 million years of selective pressure. And it would look different, perhaps radically different, to an observer with different eyes. This does not mean that vision is unreliable or that the world is an illusion.
Your visual system is exquisitely well calibrated to the ecological demands of a primate living in a world of sunlit objects, and it does its job with extraordinary fidelity. But fidelity to what is useful is not the same as fidelity to what is complete. The ultraviolet patterns on a flower, the magnetic field lines of the earth, the infrared glow of a warm body in the dark, the circularly polarized light reflecting from a mantis shrimp's shell, the electrical field generated by a fish moving through water. All of these are real physical phenomena. All of them are being detected by some visual or sensory system somewhere in the animal kingdom. And none of them are part of your visual experience. The world is larger than what you can see. It has always been. Infrared vision is rarer, but exists in some remarkable forms.
Pit vipers, pythons, and boa constrictors have facial pit organs that detect infrared radiation, allowing them to form thermal images of warm-blooded prey in complete darkness. The vampire bat has a similar system, with infrared-sensitive receptors in a patch of bare skin near its nose. These infrared detectors do not operate like eyes in the traditional sense. They do not use lenses to focus light onto a retina. They work more like thermal cameras, with the spatial resolution of the image limited by the number of individual detector elements in the pit. But the result is a genuine thermal image of the environment, accurate enough to allow a striking pit viper to target the warmest part of a mouse's body in complete darkness. The deep sea is a world of almost total darkness, broken by bioluminescence, and the visual systems of deep-sea animals have evolved in response to these conditions in ways that push the limits of photon detection. Some deep-sea fish have eyes so large relative to their body size that they look almost cartoonishly disproportionate, but the size is functional. In deep water, where photons are extraordinarily scarce, a larger eye aperture collects more photons, allowing the animal to form an image in conditions of near total darkness. The giant squid, Architeuthis dux, has the largest eyes of any living animal, sometimes exceeding 1 foot in diameter. These enormous eyes are thought to be an adaptation for detecting the faint bioluminescence produced by sperm whales as they move through the water, giving the squid early warning of an approaching predator from a distance at which escape is still possible. At the other extreme of the light environment, some animals have eyes adapted to deal with an excess of light rather than a shortage. The desert-dwelling mantis shrimp lives in shallow tropical water, where light intensities can be intense enough to bleach photopigments faster than they can be regenerated, effectively blinding an animal with normally adapted eyes. The animal's 16 photoreceptor types include mechanisms for photoreceptor protection and rapid regeneration that allow it to function normally in light intensities that would overwhelm most other visual systems. Now consider what you are doing with your own eyes at this moment. You are reading, which requires resolving text at a scale of perhaps a millimeter, at a reading distance of perhaps 18 inches, detecting sufficient contrast to distinguish dark letters from a lighter background, tracking the smooth horizontal motion of your gaze across lines of text, and, simultaneously, maintaining peripheral awareness of your surroundings, all while your visual system automatically adjusts the gain of your photoreceptors in response to moment-to-moment changes in local illumination.
suppresses the visual interruption that would otherwise result from your blinking roughly 15 times per minute, and constructs from two slightly different two-dimensional images on two retinas a single, seamless, three-dimensional model of your environment. You are doing all of this without any conscious attention to the process. Your visual system is running this extraordinary computational operation silently in the background of your awareness, reporting only its conclusions while hiding all its work. The neural hardware required for this processing is staggering. The optic nerves from your two eyes carry approximately 2 million nerve fibers each, a combined channel capacity greater than all the other sensory nerves in your body combined. Roughly 30% of the human cerebral cortex is devoted primarily or substantially to visual processing. The brain area called V1, the primary visual cortex, contains approximately 140 million neurons, each connected to thousands of others in circuits of immense complexity. The processing cascade that transforms the raw signal from your retinal photoreceptors into the experience of seeing begins with simple edge detection in V1 and proceeds through at least a dozen distinct cortical areas, each specialized for a different aspect of visual analysis: motion, color, depth, object recognition, face processing, spatial navigation. The visual brain is not a single processor. It is a network of specialized modules, each contributing a different layer of interpretation to the raw data streaming in from the retina. The investment your brain makes in visual processing reflects the investment evolution has made in vision as a primary information-gathering strategy for our lineage. We are, by the standards of the animal kingdom, unusually vision-dependent creatures. Many mammals rely more heavily on olfaction or hearing than on vision. Dogs experience the world primarily through smell. Bats experience it primarily through echolocation. Moles live essentially without functional vision. But primates generally, and humans specifically, have invested heavily in visual capability at the expense of other sensory modalities. We have relatively poor noses compared to most mammals, relatively modest hearing ranges, limited tactile sensitivity compared to rodents, and essentially no electroreception or magnetoreception. What we have instead is a visual system of remarkable capability, with trichromatic color vision, excellent spatial resolution, sophisticated motion detection, and the neural machinery to extract from visual scenes a level of semantic content, understanding not just what is there, but what it means, that no other animal matches.
This visual dominance in human cognition has shaped language, culture, and thought in ways that run so deep that they are almost invisible. The very metaphors we use for understanding are visual. We say we see what someone means. We shed light on a problem. We gain insight. We look for clarity. We illuminate an argument. We are enlightened. When we want to emphasize that we understand something deeply, we say we have seen it. When we want to express confusion, we say we are in the dark. The conceptual vocabulary of understanding is built almost entirely from the vocabulary of vision, which suggests something about how deeply visual experience is woven into the architecture of human thought. It is worth pausing here to consider just how much of physical reality your visual system does not detect.
The electromagnetic spectrum runs from gamma rays at wavelengths of less than 1/10,000,000,000th of a meter to radio waves at wavelengths of kilometers or longer. The slice of this spectrum that your photoreceptors respond to, the slice we call visible light, runs from roughly 400 nanometers at the violet end to roughly 700 nanometers at the red end. As a fraction of the full electromagnetic spectrum, this is a band so narrow that the analogy of a credit card's thickness against the full width of the continental United States is only a slight exaggeration. Radio waves pass through your body constantly, carrying signals from hundreds of broadcasting stations, cell towers, Wi-Fi routers, and satellite transmitters. Microwaves permeate the atmosphere. Infrared radiation radiates from every warm object in your environment, painting a thermal picture of the world around you in a frequency your eyes cannot detect. X-rays and gamma rays arrive from deep space and from radioactive materials in the ground. All of this information is present. Your visual system ignores all of it, reporting only on that thin slice of reality between violet and red. You are not seeing the world. You are seeing a highly curated, carefully selected excerpt of the world, one tuned by 400 million years of evolution to the specific frequencies that happen to carry the most relevant survival information in a sunlit terrestrial environment. Other animals report from different excerpts. The pit viper reports from the infrared. The bee reports from the ultraviolet. The shark reports from the electrical field. The bat reports from reflected ultrasound. The migrating bird reports, apparently, from the magnetic field, with a visual system that may actually represent magnetic field information as patterns of light and dark overlaid on the optical image, allowing the bird to see its compass heading as literally visible information rather than as a separate sense. Each of these animals is building its model of reality from a different selection of physical signals, and each model is accurate and functional and completely different from yours. What does it feel like to be a mantis shrimp? What is the phenomenal experience of having 16 photoreceptor channels rather than 3? Of seeing circularly polarized light that is invisible to virtually every other animal in the ocean? Of conducting private conversations in a channel of the electromagnetic spectrum that constitutes a kind of visual secret language? We genuinely do not know. The philosophical problem of understanding what experience feels like from the inside for an organism very different from yourself is one of the hardest problems in all of philosophy. And it applies with particular force to vision because visual experience is so central to human consciousness and so varied across the animal kingdom. The philosopher Thomas Nagel asked in a famous 1974 essay what it is like to be a bat, experiencing the world primarily through echolocation rather than through vision. His answer was that we cannot know, and that this inability to know reveals something important about the limits of objective scientific description as a complete account of subjective experience. The same question can be asked about the mantis shrimp, the scallop with its telescope eyes, the deep-sea fish straining to form an image from a handful of photons in the nearly complete darkness of the abyss. The most recent chapter in the story of vision is being written not by evolution, but by engineering. Bionics researchers have been working for decades on artificial visual systems that can restore some degree of sight to people who have lost it. The first-generation retinal implants, devices that replace lost photoreceptors with an array of electronic pixels stimulated by a camera, have restored functional, if limited, vision to some blind patients. The resolution is low, perhaps 60 pixels at best, which is enough to detect light and dark and simple shapes, but not enough to read text or recognize faces. But the trajectory of improvement has been steep, and more sophisticated neural interfaces are under development that aim to bypass the retina entirely and stimulate the visual cortex directly, potentially allowing much higher resolution and a more complete restoration of visual function. More speculatively, researchers have begun to explore whether the human visual system could be extended beyond its current spectral range by genetic modification. The human eye has 3 types of cone photoreceptors, but it has room for more. Some women carry 4 types of cone photoreceptors due to a genetic variant, and at least some of these tetrachromats appear to have genuinely enhanced color discrimination, perceiving distinctions between colors that appear identical to trichromatic observers. This suggests that adding cone types is biologically feasible and functionally meaningful.
If it is possible to add a cone type sensitive to ultraviolet light, the human visual system might be extended to see in ultraviolet without losing any existing capability, simply by adding a new channel. The Mantis shrimp's 16-channel system might represent not an upper limit, but a direction of travel. Evolution has spent 400 million years exploring the space of possible visual systems. We have barely begun. The story of the eye begins then with a protein, a molecule called opsin embedded in the membrane of a single cell somewhere in the warm, shallow ocean of the Precambrian, waiting for a photon. When the photon arrived and the retinal snapped and the electrical signal fired, nothing in the world changed. The cell reported that there was light. This was all it could do. It was as far from an eye as a single transistor is from a computer. But it was the beginning. From that beginning, evolution built the compound eye of Anomalocaris, with 16,000 facets scanning the Cambrian Sea for movement. It built the calcite lenses of the Trilobites, engineered to minimize optical aberration using principles a 17th century mathematician would later independently derive. It built the reflecting telescope of the scallop, the 16-channel spectral analyzer of the Mantis shrimp, the infrared pit organs of the pit viper, the magnetic compass overlaid on the visual field of the migrating warbler, the enormous light buckets of the deep-sea giant squid straining to see in the darkness of the abyss. It built them 40 separate times, from scratch, in 40 separate lineages, each time arriving at the same fundamental conclusion. Light carries information, and information is survival. And it built your eyes. 2 camera-type organs, each containing approximately 120 million photoreceptors, connected by 2 cables of 2 million nerve fibers each, to a processing system that occupies roughly 1/3 of your cerebral cortex. Eyes that can detect a single photon in complete darkness. Eyes that can resolve text at a scale of a millimeter from arm's length. Eyes that can track a moving target, adapt to a million-fold range of illumination intensities, construct a 3-dimensional model of the environment from 2 2-dimensional projections, and perform all of this processing so efficiently that the experience it generates feels not like computation,
but like simply opening your eyes and seeing the world. That feeling, the feeling of simply seeing, is perhaps the greatest illusion your brain performs. What you experience as direct, unmediated contact with reality is actually the end product of an enormously complex reconstruction, a model built from incomplete and ambiguous data by neural circuits shaped by 400 million years of selective pressure. You are not seeing the world. You are seeing your brain's best guess about the world, constructed from the narrow slice of the electromagnetic spectrum that evolution decided, long before you were born, was worth paying attention to. The first eye on Earth was a photosensitive patch, a smear of pigment on a single cell. It could tell its owner that light was present and nothing else. Between that patch and the eyes you are reading with now lies the whole of animal evolution. The Cambrian explosion, the rise and fall of the trilobites, the development of the vertebrate nervous system, the colonization of the land, the age of dinosaurs, the emergence of primates, and the long cognitive journey that produced a species capable of asking, while looking up at the sky with those eyes, what the universe is and how it works. The question of what the first eye was is, at its core, a question about the origin of the world as it is experienced, rather than simply the world as it is.
Before eyes, the universe existed in profound objective indifference, its photons streaming through the void and bouncing off surfaces with nowhere in particular to go, carrying information that no one was reading. Then, in a shallow Cambrian sea, a photon struck a molecule of retinal. The molecule changed shape, and for the first time in the 4 billion-year history of life, a small piece of the universe looked back. Everything you see today is the consequence of that moment.